Hello students, in this video we are going to learn about sum of absolute difference using RTL design. In our previous video we have seen a case study named laser based distance measurement, and we have also seen another case study named as soda dispenser machine. So in all these things, we have used certain steps which are quite common in all the RTL design. So what was those steps? We first calculated, or we have formed or captured the behavior using high level state machine. We proceeded to find the data path components. We created a data path. After that, we have connected the data path with the controller by knowing the controller's input and output, and we derived an FSM from high level state machine. By connecting our data path with the controller, we ended up at the custom processor or our required circuit. Okay. Now with the same steps, we are going to form or find a processor which is sum of absolute difference. What is the sum of absolute difference, SAD? Okay. It is not sad, it is, you can be happy when you do this RTL design because it is quite easy. Usually the sad difference or the sum of absolute difference, which is nothing but modulus of x plus y. You would have studied this. Modulus of x minus y. 2 points you take, find the difference and the modulus. Okay, that is nothing but the absolute difference. Now in image processing, usually we'll be having this SAD technique, which is a measure of finding the similarity between the image blocks. Okay, it is calculated by taking the absolute difference between each pixels in the original block and the corresponding pixel in the block which is being used for comparison. If suppose you would have studied in image processing, the image will be consist of various pixels. Suppose I'm having a first pixel, I will be calculating the pixel value of that particular frame and the second frame, and in that second frame the corresponding pixel. If it is first pixel, in that second frame also it will be the first pixel. Find the intensity value or the intensity difference between both the pixels, and you just take this difference, or you take the absolute difference between these two pixel values, and that is nothing but the sum of absolute difference. These differences will be summed to create a simple metric of block similarity. Actually, this will, if I explain you what actually is a pixel and what is the similarity or what is the image processing and all those things, intensity value, we will be moving or deviated away from this RTL design. So with the hope that you all know what actually these terms are, I'm moving forward and using this SAD or the sum of absolute difference, we are using that particular SAD for video compression technique. So these days we have many videos, and if suppose I want to download any video, that video will be consisting of lot of space, and so it will take a lot of time for me to download the particular video, or it may buffer if I want to read it online. So for such cases I can go for the video compression technique. Thereby I can compress it. So I'm going to, in this RTL design, our ultimate aim is for compressing my video by using the sum of absolute difference using RTL design. Is it clear? Thing is, we are going to compress the video using the sum of absolute difference technique by using RTL design process. Okay. So first thing is, you must know what actually is a video compression. You know, video will be completed, or it is a series of frames. It is nothing but pictures. Different pictures will be summed together to give you a video. You all know that each frame will be for maximum of 25 seconds frame. So thing is, like, suppose the first frame is there, and for sending a particular frame I need 1 megabyte. Okay, and the second frame is there, or the second image is there, and that second image is also taking 1 MB, which means 2 MB is needed for transmitting 2 frames. Okay, so what is the difference? I'm saying, suppose frame 1 is having a ball and frame 2 is also having a ball, because it is a video, but what is happening, the frame 2 is having a ball in another pixel location or in another location. So the one remaining everything, the mountain and the water which is on the down, everything is the same. The only difference is the ball is being moved. So instead of sending the entire frame, if I send the entire frame 1 and 2, I need 2 megabits. But what is the difference when I compare frame 1 and frame 2? Just the ball has been moved. So I am passing, my ultimate aim is I want to pass the information that my ball has been moved. For that information, or for passing that particular information, I am sending the entire frame that is of 1 megabyte. So what I must do, I must compress. What technique I'm using for compressing? Sum of absolute difference. So what I'm finding is the ball that has been moved from one particular location, say X. Okay, consider this location as X and one more location is Y. I just want to find the difference between these two locations, between this location to the new location. The difference of 2 from 1 will be calculated, and that particular difference will be of small byte, which is 0.01 megabyte. It is so less, so I'm just sending the difference. Now this difference will be added with the digitized frame 1, which is 1 megabit. So 1 megabyte plus 0.001 megabyte, which is so less when compared with 2 megabit of information. So calculate the difference of the pixel, or calculate the difference between the two, and sum it with our original frame and pass it. So usually most frames are similar to the previous frame. So compression idea is just send the difference from the previous frame. So we will be having a difference, okay, and this difference will be summed with the previous digital frame. So 1 megabyte plus 0.01. Then 1 megabit, because we know video, consider a particular video is having 2 images. So 1 megabit plus 1 megabit, 2 megabit, previous case. But using this SAD technique, I'm having 1 megabit plus 0.01 megabit. So is it clear? So now we are going to determine, suppose there are 2 frames that are similar enough to send the difference for the second frame. So now I have done a compression or the comparison, and I have found the absolute value of the difference for each array element. Now there may be difference of different pixels might have changed. So in such cases, if suppose not only a ball, if all the entire background, everything is being changed, in such cases, if I find the difference between all this thing, it will again take a lot of time. So I will be having a threshold. If my sum of those differences is above a threshold, I can completely send the data, or else I have to use a difference method, which is using another technique that I am not describing over here. So ultimate aim of our RTL, be clear, in RTL design, we are going to find the difference between 2 pixels, and we are going to add it with the original frame, and we are sending for the process of video compression. As of now, this is all sufficient before we get into our RTL design. So what I told, that we are having 2 frames, this 256 byte array, which is A, and another frame which is B, and SAD is nothing but the sum of absolute difference component. When a go signal comes, okay, it is going to sum the difference of the element pair A and B, and that is going to give you that output, that is the sum. So when a go comes, A and B's difference will be found, and that will be summed together, and it will be given into the output register, which is SAD's output. Okay, that is going to give the sum of that absolute difference of A and B. So this is the component or the processor of your SAD. So we must know how to find the high level state machine of this SAD. What is this SAD? A and B are your inputs, and a go signal comes. Difference is found by subtracting A and B. After that, I have to add it with the previous frame, and I need to store that value, and that will be sent in the output. Now, what are the inputs do I need? Inputs are A and B, which is 256 bytes memory. Okay, and now another bit is there, which is go bit. Just go, and just also an input. What is your output? Only output is the sum. that is SAD. That is, I'm giving it as a 32-bit output, and I'm using some local registers. Okay, for what? For storing your sum. Okay, as well as for your I bit. What is this I? We know the value of, suppose it is a memory, you will be having certain array. A and B are nothing but it is 256 byte array. So for storing the array value, just 1, 2, 3, I is equal to 1. I is equal to, if you know the image processing, you will be having that pixel values. Okay, I comma j, I comma j. So which I can be starting from 0, 0 comma 0, 0 comma 1. It will be moving on. So the particular pixel means it is starting from, because it is an array, it is a collection of elements. So it is 256 array. So I need 8 bits. So I am giving 9 bits. So I is of 9 bits. And then what is this? First we shall move on into the high level state machine. We have declared the inputs and outputs and the local registers also. Okay, now what we want to do, first go wait in S0 state. I am waiting for my go signal to come. My go signal has come. Once the go signal has come, what I need to do, I have to go to the next state. What is the next state? S1. In S1 state, what I need to do, I have to make my sum register is equal to 0. Okay, the sum is made equal to 0 and the index I must start from 0. So sum is equal to 0 and I is equal to 0. And then what I need to do, I need to go to next state after initializing my sum and index. And in that S2 state, I must check whether my I is greater than or equal to 256, because it is 256 byte array, whether I have completed finding the difference of all this 256. So if my I is greater than or equal to 256, what I need to do, I will move out. If not, if my I is less, suppose if I is equal to 0, I will move on into the next state, which is S3. So until unless my I becomes greater than 256, I will be moving into S3. In S3 state, I will be finding the sum, and that sum is nothing but we are going to add the difference to the sum and we are going to increment our I. So I is equal to I plus 1. What is this? Sum is equal to sum plus absolute of A of I minus B of I. If suppose my I is equal to 1, A of 1 and B of 1 value will be there. Both will be found. We will be finding the difference and we'll be finding the absolute of that difference, and we'll be summing that absolute difference with the previous original image. So both the things will be added and that will be stored in a register called the sum. And after finding the sum, I will be incrementing my I. Again it will go to S2. Then now I is equal to 2. In that same way will happen. So A of 2 minus B of 2, absolute has been found, that has been summed with sum, and previously some value would have been there. That sum is added with this sum and some new sum will be stored. Again my S is incremented. It will continue until my I is becoming greater than or equal to 256. Once it crosses 256, I will be moving into S4. In S4, what I need to do, it is done state. I will be writing my output into the SAD register. So what is the data that has been stored in sum will be stored in the SAD's register, and that is going to act as the output. And now this difference, okay, I will be having some difference. This difference, if it is more than a threshold, I will completely send the frame instead of sending the difference. If not, I have to use the difference technique that we are not going to learn, because this is just for creating the RTL design of the sum of absolute difference. So this is the state level, high level state machine. There first we started with the state S0. A go signal is coming. We are going into the next state. We are initializing our sum register to 0 and the incrementing register I register is also to be equal to 0. Once everything is initialization has been completed, moving into the next state. In the next state, I will be checking whether my I is becoming greater than 256 or it is less than 256. If it is greater than 256, I will be sending the data that is stored in the sum to the register. If not, what I will do, I will be calculating the absolute difference and I will sum with the previous value, and that will be stored in sum, and I will be incrementing the counter, or I will be incrementing the I register. I is equal to I plus 1. And finally, after completing the sum, and that value will be stored in the register and it will be sent into the initial step of S2. Again, the processor will start to execute after getting a go signal. So this is the behavior, or I have captured the behavior of my circuit or the custom processor with the help of high-level state machine. I hope you understood the video. In the next video, we shall see how to connect a data path and how to connect it with the controller and how to derive our FSM in brief. So I hope you understood this video. Thank you.